So here's our setup. We're going to look at Adam and Eve, who each have an initial endowment of 10 leaves and 10 figs. We have a utility function for both Adam and Eve, and we want to find the equilibrium prices and quantities. So let's go through our 4 steps that we talked about to solve this problem. Step 1 is we're going to solve the Lagrangian. And we're going to do this. I'm going to show you the work for Adam. Eve is analogous. You can follow that on your own, and we'll show the answer to what we do had we done it for Eve. But what we want to look at for Adam is we want to maximize. We want to choose the number of figs and leaves that Adam consumes. Here the A subscript refers to this is the leaves that Adam will consume. If it were Eve, we'd have an E subscript. And we want to maximize his utility of Adam such that if he were to sell all of his figs from his initial endowment and sell all of his leaves from initial endowment, that would be how we define his income. So that is the constrained optimization problem. So I'm going to write that out as a Lagrangian. So Lagrangian for Adam is equal to his utility function, which is 2 times the log times the number of figs that Adam consumes, plus the log of the leaves that Adam consumes, plus lambda times our binding budget constraint. So there is our Lagrangian that we're going to solve out for step 1. So let's go ahead and solve for the first order conditions. So the first order condition with respect to figs for Adam would be 2 divided by figs for Adam. There's no F or no figs in this equation, so that is going to cancel out, or it's going to be 0, minus lambda price of figs equals 0. The other first order condition with respect to leaves will give us 1 over LA minus lambda PL equals 0. And then our third first order condition, as we take the partial derivative with respect to lambda, is our budget constraint as follows. So those are our first order conditions. Now from this, the strategy we're going to use is we're going to take the first equation, divide it by the second. So I'm going to bring this over to this side and then divide each of those equations. And that's going to lead me to get 2 FA divided by 1 over LA is equal to the ratio of the prices, because the lambdas will cancel each other out. So I can then rewrite this as 2LA over FA is equal to the ratio of the prices. Now from here, the step is I want to solve for either FA or LA, and then if I solve for that, plug that back into the third order condition to solve for the other one, or the third first order condition. So in this case, I'm going to solve for FA. So FA is equal to 2LA times the price of leaves over the price of figs. And now I'm going to take this equation here and plug it into that FA within our budget constraint. And so that's going to lead us to IA minus PF, and now I'm going to put in what we had, 2LA, price of leaves, price of figs, minus PLLA equal to 0. And we'll see that different things will cancel. So those will cancel, and we have like terms over here. And so I can combine and then solve for LA. And so the number of leaves that Adam consumes is equal to his income divided by 3 times the price of leaves. All right, so now we've solved for the optimal amount of leaves that Adam consumes as a function of income and price. So if we put this into the third first order condition, this will then allow us to solve for a function for f of a, or the figs that Adam consumes, as a function of income and prices, which is equal to 2/3 income divided by price of figs. And so this is our intermediate steps of solving the optimal quantity in terms of income and prices. But we want to take the next step is to solve for LA and FA in terms of only prices. Okay, and so this is where we're going to look at the initial endowment. And so we know that the income of Adam is equal, and this is coming from our budget constraint, is if he were to sell all of his initial endowment at the price of figs and sell all of his leaves at the price of leaves, that would be the amount of income he has. Right? And so this is going to be helpful for us because now we can take this income of Adam, which is a function of prices, and plug that into the income above. And so from that we can get that the optimal amount of figs for Adam as a function of only prices is equal to 2/3. Now the income, so that's 10 PF plus 10 PL divided by PF, and that's the optimal income for Adam, or the optimal demand for Adam. And I can carry those through. So this will be 20 PF plus 20 PL divided by 3 PF. And so that's the optimal amount for Adam. I can do the same thing to find the optimal amount of leaves that Adam demands. And this is that income measure, 10 PF plus 10 PL over 3 PL. And so now these two equations here are the optimal amount of consumption for the optimal demand for Adam as a function of only prices. Similarly, I can do the same thing for Eve. Is I can look at solve the same steps I'd go, but using Eve's utility function, I could show that the optimal amount of demand for Eve is equal to 10 PF plus 10 times the price of leaves divided by 3 times the price of figs, and that the optimal amount of leaves for Eve is equal to 20 PF plus 20 price of leaves over 3 PF. So those right there is the end of step 1, where we have solved for the optimal demand for Adam and Eve. But we don't have our prices yet, so we want to be able to solve for what the prices will be. So let's go ahead to step 2. So step 2 is substitute into the market clearing conditions. What this means is that the demand for figs for the entire market should equal the supply of figs for the entire market. Well, let's start with the supply. That might be the easier one. Is Adam is endowed with 10 figs, and Eve is endowed with 10 figs. So in this exchange economy, there are only 20 figs that can be exchanged. Well, the demand is simply the demand that Adam has plus the demand that Eve has needs to equal this market clearing condition. And so I can use this to say, well, I know the demand for Adam and I know the demand for Eve. We just solved those. And so here's where we can then plug in the demand for Adam, which we solved previously for figs, is 20 PF plus 20 PL divided by 3 times the price of figs plus, and now we're going to put in the demand for Eve that we just solved for figs, which is 10 PF plus 10 PL divided by 3 PF, and this has to equal 20. And so what we've done here is we've used the market clearing conditions to give us an equation with 2 unknowns. We don't know the price of figs, nor do we know the price of leaves. And so this will then lead us into step 3. Or actually, before we get to step 3, let's go ahead and simplify this real quick. And so this can be simplified into 10 PF plus 10 PL divided by the price of figs is equal to 20. So this is what we get for the market clearing conditions. Now we go to step 3, is we're going to normalize one of the prices. So we're going to normalize one price. And in this case, we're going to say, let's let the price of leaves to be equal to 1. So by normalizing that, it takes this market clearing equation that we had and is going to allow us to rewrite it as 10 times the price of figs plus 10 times 1, which is the normalized price of leaves, over the price of figs, which is equal to 20. And now we have one equation with only one unknown, and so now we can solve for the price of figs. And so this is what step 3 will give us. And so I can get 10 PF plus 10 equals 20 PF by bringing the denominator to the other side. And this is going to solve fairly easy. The optimal price of figs is equal to 1. And because we normalize, the optimal price of leaves is going to equal to 1. So here we have established and solved for our optimal prices. So this is the optimal price within this exchange economy of how much it's going to cost for each fig and each leaf. Now that we have those optimal prices as specific numbers, we come to step 4 and we use equilibrium prices to find equilibrium allocations, which means we take the demand from Adam and Eve. So again, we had the demand for Adam was equal to, in terms of figs, was let's get the right marker. Here we go. 20 times the price of figs plus 20 times the price of leaves, all over 3 times the price of figs. So that means we can rewrite this as 40 divided by 3, which is equal to 13.33. Another way we can think about this was our intermediate step that we did over here, is that the optimal amount for Adam in terms of income and prices is 2/3. So we can use that as well to say that F of A is equal to 2 times the income, 3 times the price of figs. Well, if remember, the income for Adam was 10 times the price of figs plus 10 times the price of leaves. And so this means that Adam's income is 20. So we can use this as 2 times 20 over 3 times 1, which is the same number we had before, 40/3. And so we can use that same equation here, that either using this equation we had for optimal amount, or these equations here for optimal amount, either one will work to solve for his optimal amount of leaves, and we'll get 20 divided by 3, or 6.67. Now for Eve, we can do the same thing, and using her equations, we get 6.67. And the amount of leaves for Eve, that's optimal, is equal to 13.33. So this here is our optimal allocation, or the demand for Adam and Eve. So we have our prices here, and we have our quantities here. Now we could even draw this in an Edgeworth box. So let's show how this would look in an Edgeworth's box. So if I draw the box here, and I draw Adam over here, and Eve over here, and then I call this amount here, the number of figs that Eve consumes, and the amount over here, the number of figs that Adam consumes. This vertical distance is the number of leaves that Adam consumes, and this distance here is the number of leaves that Eve consumes. Now, because we know that the total supply in the economy, we know that there are 20 figs that Adam consume at most, and 20 figs that Eve can consume. There's also 20 leaves, and 20 leaves that each of them consume. That's the total endowment that they could do. But what we find is the optimal answer for Adam is that he will consume 13.33 amount of figs and 6.67 of leaves. So that means that is his optimal allocation, is right here, which means that if we draw his indifference curve, that's the indifference curve that's going to maximize his utility based on his optimal amount of consumption. Now for Eve, she's going to consume 13.33 quantity in leaves and 6.67 quantity in figs, which leads her to this exact same point, and that's the point where her indifference curve is going to be tangent to Adam's indifference curve. So this is where we can draw the Edgeworth box and show the optimal allocation. And this is where we'll look at, is it Pareto efficient? If we were to take any amount away from Adam, or can Adam become better off without taking away from Eve? And the answer is no. Vice versa, Eve cannot be better off without taking away from Adam. So that is a Pareto efficient allocation. And this is the overall solution, the graphical representation of the solution to this empirical example of the Edgeworth box, or of general equilibrium in an exchange economy.